Great. Thanks again for the introduction. Are there any questions that arose from the coffee break or anything? All right. Well, I hope you enjoyed the sort of fluffy first lecture introduction, because now we get into some nitty-gritties. So I want to discuss the conjecture, random matrix conjecture of mine, which implies this Peterson-Thom conjecture. So to talk about that, I have to talk about strong convergence, although it's more or less already been alluded to. So basically, you can formulate this as an actual topology on the space of laws, but I won't do that. So let's say we have some sequence of tracial von Neumann algebras and some other tracial von Neumann algebra. And I give some R tuple of sequence of R tuples in these tracial von Neumann algebras, and some R tuple in the sort of limit tracial von Neumann algebra. Then we say that the law of xn converges to the law of x strongly if, and I should warn you that different authors are going to take different sets of definitions. So this is my, well, mine plus some other people's, but the lower bound is that it's mine convention. So we say that this converges strongly if the law of xn converges to the law of x weak star, which is what we talked about last time. Just take traces of polynomials in the xn, that converges to the relevant trace of the polynomial x. And for every non-commutative star polynomial in our variables, if I evaluate this polynomial on the xn's, and I take the operator norm, then that converges to the operator norm of the polynomial evaluated on the tuple x. Okay. So one thing I should have mentioned last time, just to give some sort of last little bit of fluff here, which is that if I took some self-adjoint star polynomial, okay, the convergence of the laws tells me that I have convergence of these spectral measures. So this is the spectral measure with respect to the trace tau n, and then you have the limiting spectral measure with respect to the trace tau, weak star. Well, this, again, plus operator norm, uniform operator norm bounds. This is the thing I said last time, that if you don't have uniform operator norm bounds, you can't do anything good. So, okay. Whereas strong convergence, and this is really the same as saying that for all p equals p star. So for every self-adjoint polynomial, I have this weak star convergence of spectral measures, whereas strong convergence is the same as, well, weak star convergence, weak star, plus, again, for every self-adjoint polynomial, the spectrum of p of xn converges to the spectrum of p of x in the Hausdorff sense. So the spectrum is a non-empty compact subset of the complex plane. So I have this Hausdorff metric between them. And so this is the same. So again, for sort of the random matrix people, weak star convergence can be funny. I can say that my approximate starts to look the same as the limiting distribution, but then I have some minor fuzz way out here that asymptotically doesn't contribute much, whereas strong convergence says that that can't happen. If I pick some small neighborhood, eventually the support of the spectral measure here has to be contained in the support of the limiting thing. So, okay. So I'm going to sort of start by trying to state the, actually maybe I'll just start with that. So strong convergence for random matrices has a long history. I won't, again, be able to get into all of it. But the first sort of paper in this direction was Hagerup-Thorpe-Bjornsen in 2005. And there's also some nice paper by Hannah Schultz, again in 2005. And then there's lots in between, but I'll just mention a few. Collins, Mall, 2014. It looks like I forgot the date for this. I think it was also 2014, and also Mall's paper in 2014. And then there's been a bunch of more recent ones, which is going to be the subject of this conference, and a few which I'll mention. So I'm going to formulate a conjecture which I proved implies this Peterson-Thom conjecture. So I'm going to call this tensor HT. For Hagerup-Thorpe-Bjornsen in tensors. Okay. Great. And I'm only going to state it for the Haar unitary ensemble, although for purposes of implying Peterson-Thom, it's also fine to do it for the GUE. But just to simplify the discussion, I'll just talk about Haar unitaries. Okay, so the statement is this. So fix some natural number R. U1n to URn, V1n to VRn. These are going to be 2R IID elements n by n unitaries, and each are distributed according to the unique Haar probability measure on the unitary group. Okay, and so just for whatever reason, which will become apparent shortly, I've labeled the first R of these as U's and the second R of these as V's. We'll keep this on the board. Oh, I should try to have the statement here, but can I do that? Probably not. Okay. Well, so the statement is, actually, let's try. So the statement is that if I set UN to be the tuple of the UIs, so this is UN is an R tuple, the VN is also an R tuple, then I want that the law of UN tensored with the identity on n by n matrices, and the identity on n by n matrices tensored with the VNs. So I sort of stick the U's into the left tensor factor and the V's into the right tensor factor. That this should converge as n goes to infinity strongly to the law of U tensor 1 tensor U, where U is an R tuple of freely independent unitaries, and to save space, I won't write it on the board. They're freely independent unitaries, and each of their spectral measures should be the Lebesgue measure on the circle. Okay, so they're just, you can just view them as standard unitary generators of the free group factor. Now, like I said, there's a GUE version which people who know how to modify it know how to modify it, so I won't say it, and for my purposes, it's also fine. Okay. So I don't know, maybe I should say a bit about this. And again, unfortunately, now I have to move this, right? So the left-hand side is inside n by n matrices, tensor n by n matrices. And the right-hand side is inside the C-star algebra generated by U, tensor the C-star algebra generated by U. And for those of you who are not operator algebraists in the audience, that will mean what you think it would mean. And for those of you who are operator algebraists in the audience, know that I have to specify what tensor product I'm talking about. And so this is the min. Okay, but basically, if you represented them spatially, it's what you get by spatially representing in the Hilbert space tensor product. And the other thing I want to say about this is that a nice way to view this that kind of highlights a bit what's going on is that, of course, this is just bounded operators on n by n, on the L2 space of n by n matrices with respect to its trace, where I have this act by sort of left multiplication and this act by right multiplication by the transpose to make it an actual star homomorphism. And so this is somehow saying that, like, if I left multiply by these u's and I left multiply by these v's, and I want to understand norms of polynomials in that, again, secretly, there's a statement about traces of polynomials, but it already follows from the weak star convergence. So it already follows from Voiculescu's work. So if we want to take polynomials and sort of left multiplication, right multiplication, it converges to the appropriate polynomial on left multiplied by u tensor 1 and right multiplied by 1 tensor u.
But is it possible to purely probabilistically say, what do you claim about these matrices? Just without any non-commutativity, is it possible to say? Is it just impossible to state somehow?
I'd have to think about it. I mean, this is one advantage that actually, related to things I'm trying to think about now, one secret, even though this is hard to prove, one secret nice thing that it has is you can already guess what the limit should be. And so I think trying to formulate more purely probabilistically would get around that, and I don't quite know how to do that. One thing I do want to say about probabilistically is a bit of a subtle point. I don't want to get into too much detail on this because, again, I want to get to some of the more exciting aspects of the details. Is that, OK, so like I said, if I do this operation where I take weak star convergence, tensor with 1, and then do 1 tensor the other, that will preserve weak star convergence. Okay? It does not, in general, prove strong convergence. So there's no soft technique you could do by just saying that this operation preserves strong convergence. In fact, the fact that these are IID is very important. If I took UN equals VN here, it is simply never true. It is just false. And it happens to do with the fact that free groups are not amenable. So you really need to couple them independently. Otherwise, it's just not true. OK. And so the theorem I think that's the publication date, is that tensor HT implies PT. And there's something in between that I'll highlight as well that really is secretly the theorem. But if you prove this random matrix result, then this Peterson-Thom conjecture falls. It was asked during the break why this Peterson-Thom is a natural conjecture in von Neumann algebras. And again, it sort of has to do with a lot of prior results on strong solidity and maximal inability and so on, and Peterson-Thom's results on L2 Betty numbers and such. But also just in general, because of Kahn's very deep work, operator algebraists feel like they understand amenable von Neumann algebras very well. And so we want to sort of understand general von Neumann algebras by how the lattice of amenable subalgebras looks. Yes.
Sorry, two questions. Is the random variable in the limit, is that the same U occurring both in the U?
Yes.
Right, OK.
Yeah.
And then secondly, I didn't catch it. So is this a theorem if you replace strongly by weakly?
Yeah, but it's more of an exercise from Voiculescu's theorem. So if you take Voiculescu's theorem for granted, which is basically delete the U, delete the V's and delete the tensoring, and delete the tensor 1 and 1 tensor U here, that you have weak star convergence, it is an exercise to derive the tensor inversion. It's just sort of immediate from that. But what? Yeah, it's immediate from asymptotic freeness. But actually, it even almost doesn't, it has to do with just this operation preserves weak star convergence of laws. It's because if I take, really, I did it for arbitrary non-commutative polynomials, but if I'm taking a polynomial and some things that commute, it's really secretly a tensor of some sum of elementary tensors of polynomials. And so I just check it directly on the elementary tensors. It's sort of a very, it just, multiplication is continuous.
I think the fact that you had the same U in the limit and a U and a V before is just kind of a notational misconception, right? Because if you think about these random matrices not as random matrices, but as matrix-valued functions on the probability space. Yeah. If you take the tensor product of those two things, you get exactly two independent copies, right? Yeah. So,
sure.
So somehow or other, that's just yeah. The fact that it doesn't look symmetric between the left and the right is just a notational issue. It's not a...
Sure. So you could formulate this as strong convergence of, not random strong convergence of laws, but strong convergence of laws in like L infinity of n by n matrices with value in n by n matrices and that, yeah. Exactly, yeah. That's true. Okay. Other questions? Yeah, that's, okay. I won't write it, but we all agree. Okay, other questions? All right. So the first thing I want to say is sort of an immediate intermediate conjecture, which I call the entropy conjecture. which is that if Q inside of L of FR, if we just take any von Neumann subalgebra, then the statement that its entropy is 0 is equivalent to the statement that it's hyperfinite. Okay. Now, if you remember the join lemma that we hashed out a bit, why all those assumptions are significant last time, you will see that the entropy conjecture implies this version of the Peterson-Thom conjecture. Because what the join lemma says is that if I take the join of two subalgebras with diffuse intersection, then the entropy is subadditive under that operation. So if both of these have entropy 0 and they have diffuse intersection, then the join lemma will tell you that their join has entropy 0, and then I run this sort of backwards implication. I should mention, as discussed last time, this implication is just always true, that the content is about this implication. Yes?
One question. When tensoring with the identity, like the subscript on the law, are you just doing that component-wise through the tuple?
Yeah, just component-wise. Other questions? Yeah. So when I write less than or equal to, I mean von Neumann subalgebra with the same unit. Yeah, so this implies this is just general fact. It has nothing to do with free group factors or whatever. Yeah, so the implication, and really the way you do it is showing that if Q is not hyperfinite, then this entropy is positive. Okay, so this is sort of
Maybe one question, is it important that it's the same n?
the same n.
Size?
Yes, extremely important. It doesn't work if it's not the same size. Yeah, and so in fact, I'll get into the history a bit. Again, I'll have to sort of do an abridged version. But before proofs were announced where they had, they really did the same size and did even much better than that, like various proofs were announced where one was like n to the 2/3 or something like that, and that is not sufficient. You need both n's to be the same. If I have time to get into sort of the nitty-gritties, I can explain why, but it's important that they're the same. Otherwise, it just doesn't work.
Can I ask you a naive question as a non-expert?
Yeah.
So as a non-expert, the significance of the statement of Peterson-Thom is kind of not so clear, right?
Sure.
But that statement that you call entropy conjecture seems completely like the right question to ask. It's you can characterize hyperfinite subalgebras of a free group factor by the entropy, right? I mean, that's a beautiful statement. So, I mean, could we now ask the same question in other, for example, in other group von Neumann algebras? Like, could could we say that if you have strong convergence of some generators in a general group von Neumann algebra, that would automatically imply this? Like, is there some...
Again, depending on how much of the details I sketch that will follow, you need basically some exponential concentration of measure of the matrix models, and then you need some approximation properties, local reflexivity of the generated C-star algebra, and then strong convergence.
So in principle, if we learn how to prove strong convergence in other group C-star, it's a really C-star algebra property, right? Strong convergence is not a von Neumann algebra property, but if we learn how to prove strong convergence in other reduced groups to C-star algebras, then we would immediately have some kind of characterization of their amenable subalgebras. Yeah,
assuming correct decay of the exponential of the concentration function, which is an issue for, it's so like the proof that's given for like service groups and graphs products or whatever are not going to play so well with the concentration function as I needed, but yeah, in principle, yeah.
Can I make a comment about
Yeah.
Peter? So I think a perspective on the
I forgot
Peterson-Thom
to-
conjecture that might make its significance a little bit more apparent is that this is equivalent to saying that if Q is diffuse and amenable, and if you take the family of all amenable things that contain Q, and then just take the von Neumann algebra that you get from all of this, that's still amenable. And so this is saying that no matter how cleverly you glue together some amenable pieces, you can't really build anything interesting out of it. It's stuck as amenable. In particular, you can't build LFR itself out of just amenable pieces in this way.
That somehow the toy version that you showed at the very beginning of the last lecture goes in that direction already.
Yeah. Yeah, that also follows from the entropy. Yeah. This is getting at this Pinsker algebra and entropy, but that's a separate conversation. Okay, so in the remaining, I guess, 27 minutes or so, 30 minutes? I want to prove why this, or sketch why this implies this. Well, really sketch why this implies this, why tensor HT implies this entropy conjecture. Okay. So we're going to start with whatever my notes say next. Okay. So the idea is this. All right, let me try to give this sort of heuristically. There's sort of really just two steps. Okay? So the exponential concentration of measure that's known for Haar unitaries implies, and h of q equals 0, implies microstates collapse. So heuristically, under this exponential concentration of measure, and the rate of how exponential it is, et cetera, matters extremely, plus this subalgebra having entropy 0 means that if I sort of run Voiculescu's machinery, if I sort of build these finitary approximations of free group factors by choosing random Haar unitaries, I can think of them as like these models of my free group factor, and so, okay, it's a bit difficult to say what this actually means, but I can use them to build models of any subalgebra Q. And the combination of these two properties implies that when I use them to build models, some finitary approximates of my subalgebra Q, that all these finitary approximates are basically unitarily conjugate to each other. So up to some sort of small fuzz, and up to sort of error in the probability, the entire measure is supported on just sort of one unitary conjugation orbit. And step 2 is to say that strong convergence, basically this tensor HT property, implies that non-immutable subalgebras do not have microstates collapse. So if I take some of these stronger approximates in this sense, and really in a slightly modified sense, but again, we'll sort of not worry about this, and I use them to build approximates for some non-immutable subalgebra, then the strong convergence is going to force it so that they're actually not almost unitarily conjugate to each other. And then, of course, if you combine the two, then you're done. Okay. So what I should say here is what I mean by exponential concentration of measure. So, I mean, okay, I will just say this vaguely because I think the random matrix people kind of already know this, and like I said, this will be in one of the proposed working groups is on working through this part of the argument, that why these two steps work. And so, details are precisely given there, but basically what I want to say here is one way to think of it is that if I take some, I'll actually more or less say what I mean. If I take some, say, Borel subset, just anything that's measurable of R tuples of unitaries, and if the Haar measure of this is at least 1/2, then whenever I look at some epsilon neighborhood in, say, the 2 norm or even this orbital 2 distance, just to say this 2 norm described in the last talk, if I look at, say, the complement of that, you take the Haar measure of complement of that is at most some exponential minus a epsilon n squared.
what does it say next to her?
The epsilon neighborhood,
No, on the left part, I just don't understand the handwriting. No, left, more left.
at least 1/2. The R-fold product of the Haar measure. Yeah. Oh, I guess it's, yeah, I did it's that, sorry. Yeah. So I'm taking an R copies of unitaries, so I take the R-fold product of the Haar measure. Okay, and you can formulate a concentration function which says exactly what the right-hand side would be, and it would say that this thing decays exponentially in n squared. It's really important that this n squared matches. Yeah, if I have a different thing that's not n squared here, it sort of ruins the whole
And being
argument.
the dimension.
Yes,
I see. So that's why it's not true for graph products.
yeah. So that part is actually the key, one of the key subtleties. Okay, so I need to say a bit about this sort of inducing approximates. And what I'm going to do is sort of cheat, but only slightly cheat. So let's say I take some tuple of, say, unitaries. They don't have to be unitaries. But for simplicity, I'll take unitaries. Actually, yeah, just take any tuple of elements. Let's say I take some finite tuple of elements in this subalgebra, which has entropy 0. Then how do I sort of talk about, how do I do this thing that I mentioned where I sort of run Voiculescu's machinery and use this to induce approximates of the Q? I write the yj's as some sort of function of my generator's x. So M is generated by some tuple x. Okay. So here's the point in the talk where you're like, okay, he's lost it. What is he talking about? Can't do that. Well, you can't do that with polynomials, but you can do these with some fj's, which are from David Jekyll's NC functional calculus. And you can get around doing that, but it involves inserting in another sort of epsilon delta style statement into the statement of the theorem, which nobody wants. Okay. So you can find some function which has an interpretation whenever I plug in any R tuple from any tracial von Neumann algebra, and so it can be evaluated on matrices, and has some nice uniform L2 continuity on operator norm balls. Turns out this is always possible. And so the real statement is that exponential concentration of measure in this sense, and h of q equals 0, implies that there is some sequence of subsets of n by n matrices of R tuples of n by n matrices of unitary n by n unitaries. I guess these x's here are a free tuple, but actually my argument will work just completely generally under this exponential concentration of measure. So these are just the freely independent unitaries, each which are Lebesgue distributed. So there's some subset of there which has, again, Haar tensor R tending to 1. So it's capturing most of the space. And there is some sequence of deterministic unitaries. Or, well, really what I should say is this. OK, it's going to be slightly messy, but the limit as n goes to infinity of the inf over, say, W, which is an n by n unitary of, well, sup A1, A2, and omega n, f of A1 minus W f of A2, W star, the 2 norm goes to 0. So let me explain a bit. When I say f of this tuple, I mean apply, this is some R tuple of matrices, and consider the S tuple you get by applying each of the fj's to this. Remember I said fj's were some functions which had some interpretation on any R tuple in any tracial von Neumann algebra. And so what it's saying is that if I take any two things from this family and I compute their distance to the respective unitary conjugation orbits, it tends to 0 uniformly in the family. And the family is basically everything. So this is the precise statement of microstates collapse. So that's a bit more detailed version of step 1. Do I have a bit more detailed version of step 2? Okay, there is a bit more detailed version of step 2, but it's actually fairly detailed. So,
Can you say anything more about the omega n? Like, it's an open set, or how narrow is this thing?
Oh. I mean, what falls out of the proof is that it's some epsilon neighborhood of something in this orbital distance. So it's some epsilon neighborhood of the unitary conjugation orbit of some collection of things. Yeah, so I mean, really what it says, this is maybe a better way to say it, is actually there's some sequence of R tuples of unitaries, so that when I look at the epsilon, like the F inverse of the epsilon neighborhood of their, conjugation orbits, that has measure tending to 1.
Is there an ultra product reformulation of this result?
Yeah, but I'm trying to keep half of the audience with me, so. But yes, there definitely is. Let's talk about it after. Other questions? Okay, so let's call this star. And then step 2, I guess I am going to sort of say a few things about step 2, is to use strong convergence to negate star for Q non-amenable. And okay, I slightly lied here in that the step 2 I need is this tensor H. If you're doing it really in the general setting where you don't just want to assume Frege factor, you're just working with any von Neumann algebra, I need that the C star algebra generated by my tuple is locally reflexive, which is guaranteed, for instance, if it's exact, which is like occurs all the time in free probability. So this is a relatively minor assumption. That's a theorem of Kirchberg that exact implies locally reflexive. Okay. So how do you negate this? So let's just sort of expand, let's just expand the right-hand side here. So of course we take the norm squared. So we get these individual functions applied to my tuple, the 2 norm squared of those, and then I have this correction term twice the real part of the trace of twice the real part of the sum from j equals 1 to s trace of w star fj of a1, w fj of a2. And this should be, this should be stars here. Doesn't matter so much. Okay. And so what I do here is I just apply, right? So I just apply traciality to. So I'm just looking at my notes. Oh no, there should be a star. Yeah, there should be a star here. Right, I have to, it's sesquilinear in one variable, so there should be a star. Great, so so I would just apply traciality, or actually I guess I can just take it as given. So this term I can just think of as the sum from j equals 1 to s, fj of a1, tensored with fj of a2, complex conjugate. And if I think about this tensor action on L2 of n by n matrices, the GNS construction with respect to its trace, I apply that to W star, and then inner product with W star. Okay. Yeah. So hash, I guess, yeah. So this is this A tensor B hash C is A C B transpose. Okay. Great. Now, I mean, again, these are not literal polynomials in my generators, and they're not even things that live in the C-star algebra. But one thing that gives us some hope here is this Kohn-Hagerup characterization of amenability. Which says that Q being non-amenable, and let me cheat here and just insert the assumption that it's a factor. I don't actually need that, but just sort of to simplify the discussion, there's just a mild technical way to get around this. Let's just sort of say it's a factor just to make our life simple, in which case it actually is just Kohn. But for the non-factor case, which I also need to handle, I need Hagerup, tells me that there exists some S tuple of unitaries in Q, so that I run this same procedure along the finitary level. I get something that when I average it, the norm is less than 1. Okay. So for those of you not used to amenability in operator algebras, just think of sort of amenability in groups. Amenability in groups tells you this non-triviality of this Cheeger constant on the Cayley graph. And that can be formulated as some list of group elements so that when you average them and you take the operator norm, it's less than 1. So this is some expansion property. And what is this UJ bar? Well, sort of this is a bounded operator on L2 of M, tensor L2 of M. So L2 of M is just the space you construct from the trace. And this is really, you can just think of as left multiplication by UJ tensor 1. And UJ bar here is sort of right multiplication by 1 tensor UJ star. It's equivalent. So this is sort of the version of expansion you need adapted from the group setting to the setting of trace of one element. And OK, now you start to feel very optimistic, right? Because if these were literal polynomials, if I could find polynomials in my generators that produce these unitaries, which is like never going to happen, but if I could, then I would just be done, right? Because you see, if these are unitaries, then these quantities are each converging to 1, and when I sum them up, this is converging to 2s. And so if this quantity is converging to something that is asymptotic in the limit less than some constant times s, then I get a non-trivial lower bound. And w here was just a completely arbitrary unitary. I didn't use anything special about it. Okay. And so I guess in the interest of time, what I want to say is, well, OK, the UJs really, they're in the von Neumann algebra. They're not in the C-star algebra generated by my tuple. And so I have to sort of, this is what I think Ramon was getting at and some other people, that strong convergence is inherently a C-star question. I'm saying a bunch of stuff about von Neumann algebras. I have to find a nice way to sort of push things down into the C-star algebra. Okay, and naively, you could just approximate strongly, but that doesn't work because I have to pass the tensors. So I need to be able to approximate in a way that's going to play well with this tensor structure because I'm citing Kohn-Hagerup. So the relevant result here is what's known as locally reflexive. So C star x being locally reflexive. Well, it says many things, but one way to say it is that whenever, well, it implies in particular that whenever I look at some finite dimensional subspace of the generated von Neumann algebra, there's the sequence of completely contractive maps, so that phi m of a minus a in the 2 norm goes to 0 as m goes to infinity for all a in E. Okay. And the eagle-eyed among you, among the sort of operator algebraists here, will realize that this is also the same type of approximation that occurs in a few arguments more in the deformation rigidity direction. I think like Ozawa used this in solidity, and also appears in Kifon-Sinclair, and I'm sure lots of other places. Okay. Also, for those of you who know the actual definition of local reflexivity, you'll note that I made a few cheats here. I like use convexity, replace point WT with point SOT, then replace that with the 2 norm, and et cetera. But
for the free structure, these are the hug group maps, right?
yeah, that's true. You can. That's true. Yeah. Okay. But I need it for every finite dimensional thing. So I don't really know that my unitaries are living in yeah. No, actually, no. You're right. Yeah, you're right. Yeah. I can actually take them to be globally defined for that. That's true. Yeah. I when I wrote this, I wanted sort of the minimal hypothesis. But yeah, if you have a CMAP, then it's even easier. Okay, sure. Great. And so then what you would do here is you would take your phi m. So if I look at phi m of uj, the nice thing is that the, okay, I'm gonna have to erase a few things. Oh. So if we look at the phi m of uj, the fact that this map is completely contractive tells me that when I run the same operations with the phi m of the uj's, I still get the same bound. So a priori, I could completely wreck my bound by passing the tensors, but I don't do that because I'm approximating by something completely bounded. And then, well, these are now valued in the C-star algebra, so I can approximate them by polynomials in my tuple. And then, okay, then you sort of do just a bit of epsilon management. You replace this with the polynomials and this with the polynomials and take limits in the appropriate order. And, it's now an epsilon delta statement we would give to like a very advanced undergrad, but you wouldn't want to see done on the board. So we'll move towards readdressing the first step.
Wait, what features of this FJ did you use?
What?
FJ, this functional calculus, what features of this did you use?
Yeah, I was particularly vague about that, so let me say a bit more. First of all, they can be interpreted whenever I take any trace of von Neumann algebra and any R tuple in it. So just like I can take any R tuple and any trace of von Neumann algebra and plug it into a polynomial in R non-commuting variables, I can do it for these functions. They also have some nice uniform continuity property corresponding to our operator norm cutoffs. So implicitly, this is where these operator norm cutoffs are coming back. But if I sort of impose these operator norm cutoffs on my tuple, then basically when I interpret this function on any ball in any trace of von Neumann algebra, obeying that operator norm cutoff, like if I apply it on some tuples which have norm at most R, then they have this uniform continuity property that you hand me an epsilon, I can find a delta, so if two things are in these R balls and are delta close, in 2 norm, so if they're in the operator norm R ball, but 2 norm delta close, then their images are epsilon close. In 2 norm, and the delta only depends upon epsilon and R. It doesn't depend at all on the trace of von Neumann algebra you take. So it works for all trace of von Neumann algebras at once.
And then where was that used here?
No, it's
It's secretly used here when I sort of smush these by some polynomials. I'm varying the matrices a lot, and I want that to not cause too much of a problem.
You're using this in both step 1 and step 2? Yeah. So in step 1, you need something, right, to get concentration of measure.
Yeah.
Right? But in step 2, I don't quite see it.
So I want to.
The unitary, so it should go to just, or the FJs are not
maybe
unitary.
I am just using it in step 1. I don't know. I'm just trying to be careful here. Well, okay, secretly I'm using it in step 1 because this uniform continuity property also implies that this operation is well defined on laws. Like if I take the law of something and I can push it forward under this map F and get the law of f of x. And that's a weak star to weak star continuous operation, which more or less uses this uniform continuity. So that's secretly here to say that like the law is still, this is still asymptotically a unitary. This is still asymptotically close to a unitary, so this is 2 norm is tending to 1.
Can you essentially regard it as like a type 2-1 part of the double dual of the universal C-star algebra?
Yeah, but again, there's like a half of the room I'm trying to have things make sense to it. But also no, it's also not that. Because of the uniform continuity property.
Yeah.
Yeah, if you just did that, you wouldn't have the good uniform continuity property, which is
I mean, aren't you using it in step 2 here just to even make sense of this as you move across your matrix algebras?
yeah.
But this functional calculus is only saying something about the 2 topology. It's not, I mean, everything with the norm is taken care of by this local reflexivity, right? You
The
don't
norm
need
is, but you need the norm to have this operator norm cut off. Like you can't be, it's like, it just is not defined outside of some ball.
Let's see, okay.
Yeah. There's a potential third working group, which is to work with the L2 continuous functional calculus. All right.
What properties does this map phi m have? It just kind of disappeared and
It's completely contractive, and it satisfies this.
what does
Oh, right. So if, I have some finite dimensional thing here, so if I take like a matrix of things in this finite dimensional thing, then it lives in like matrices.
Oh, it's like completely bounded, but less than 1. Okay.
Yeah, completely bounded with CP norm at most 1. Yeah. I have what, like 3 minutes?
You have 1 minute, no, 3 minutes.
3 minutes, okay. In 3 minutes, I'll say what I can about step 1. Maybe not erase that. So for step 1, okay, unfortunately I'm erasing the thing we're trying to conclude, but the basic idea is this. Okay, unfortunately I'll have to be a little vague, but we take this f that we talked about before, this function that's encoding, my tuple in the subalgebra, and we push it forward. We push forward the hard measure with f thought of as a map on matrices, on R tuples of matrices. And this uniform continuity property I talked about tells me that this still has exponential concentration of measure at the correct scale. And so what happens from here and I'll just be super sketchy and slightly lie, is that if I take some, say, sequence of, say, Borel subsets of here, I don't actually want unitaries. Let me call this measure, this hard depends upon n, so I'll call this nu n. So if this has sort of sub-exponential size, then secretly what happens with the exponential concentration of measure is that I formulate it as this thing is at least a half implies like the epsilon thickening is like super huge, right? But in fact, anything that's not sub-exponentially small, the epsilon thickening is super huge. That's the trick. Okay. And so what you do here is you look at some neighborhood, not of your original tuple, but of the tuple in the subalgebra Y. So you look at some neighborhood, and that subalgebra has entropy 0, so I can up to epsilon and up to unitary conjugation, pack it by sub-exponentially many things. Now I'm slightly lying here. Really, I can pack it up to, you hand me some exponential decay, and I can pack it up to an amount better than that, and so I need a sort of more quantitative version of this. But roughly speaking, I can pack it up to sub-exponential size. And so just by pigeonhole principle, there's going to be something. There's going to be something in here so that its epsilon neighborhood now under this orbital distance has size, where this is some sequence. So let's say k, 1 over k squared, tending to 1. Okay, it's a slight lie. Right. But you see, once you do that, right, this new k is pushed forward under f. If I look at its inverse images, those of course have so the 2 epsilon neighborhood now is super huge. yeah. So this 2 epsilon neighborhood, and this orbital distance is now very big, right? But the new k was a push forward under f, and so what that means is I found some very large collection of unitaries, so that anytime I push them under this function f, anytime I do that, I'm unitarily close to some fixed thing. So then by the triangle inequality, any two of these things are unitarily close to each other. And then you're done. Okay, so it got a little hairy there at the end, but I'll stop here.